This one is a random question from practical experience. It says, explain briefly why starch indicator is not added until near the endpoint in the titration of iodine with sodium thiosulfate solution. So you can also do yourself a favor by watching the redox titration, specifically the iodimetric titration between sodium thiosulfate and then a solution of iodine in potassium iodide here on this channel. So we got your back. We are working for your academic success. The reason is because first is to ensure accurate endpoint. To ensure accurate what endpoint, or rather you say the reason is because the starch consumes the iodine, or you say because the starch absorbs the iodine. And remember, in this titration is required to allow the iodine present to react with the whole sodium thiosulfate. The iodine should react with the sodium thiosulfate, but if you add starch in the beginning, most of the iodine will be taken away by the starch to form a complex which is blue-black complex. That's the presence of the color you get when iodine comes in contact with starch. So the starch is used to absorb iodine. So if you add it earlier, most of the iodine will no more react with sodium thiosulfate, leading to error in the end point. Definitely, if you add it before, towards the end, that's in the beginning or in the middle of the titration, the starch indicator, the obvious thing is that less sodium thiosulfate solution will be consumed because the iodine will be taken away from the reaction. So it leads to error in the volume of thiosulfate that is used, because the starch absorbs the iodine itself to form a complex, giving us a blue-black coloration. Okay, the next question says, drops of water were found in a bottle before filling it with an acid that was used to titrate a base solution. What effect will the drops of water have on the determination of the concentration of the base? The effect is that it will lead to wrong concentration. It will increase the concentration of the base. That's the effect. And the concentration should be the wrong one. To increase it above normal. To increase the concentration of the base above the real concentration, because they said we should explain, or you can simply say it will lead to the error in the calculation of the concentration of the base. Then they say explain your answer in 3bi above. That's why will you say that it will increase the concentration of the base? The reason because the presence of water in the bottle containing the acid solution will dilute the acid solution, which will result to increase in the endpoint. Result to increase in the volume of the acid consumed by the base. Because what is supposed to be is that if the strength of the base is increased, definitely it should consume more of the acid. Then invariably, if you decrease the concentration of the base, more of the volume of if you decrease the concentration of the acid, more of the volume of the acid will be used, such that we have CAVA all over CBVB. In this case, diluting the acid more will give a more, okay, I think black should be okay here. This particular VA, if you increase it, you're automatically given chance to increase the total answer. Let's assume that we have 0.1 times 17.5 like we see previously. If you dilute the acid more, what we are going to have will be 0.1 times something like 18.5. So you have increased this the value, the VA, which automatically makes CAVA higher than CBVB, and the answer you get will be higher than normal. So that's the reason that's the possible explanation to what happens in the 3BII. Okay, we'll see question C. In that case, remember, diluting the acid will automatically lead to more of the acid being consumed. Then diluting the base will lead to less of the acid being consumed if you are titrating the acid against the base, which is always the common approach. We don't usually titrate base against acid, rather acid in the burette being poured gradually into the base. So diluting the base will lessen the endpoints, but diluting the acid will automatically increase the endpoint because more of the acid solution will be consumed. Diluting means lessening the number of moles dispersed, then increasing the water part of it. Okay, let's see the next question. Okay, over here is the next question, question C. Says a student carefully pipetted 25.0 cm cube of 0.525 mol per dm cube sodium hydroxide into a test tube and placed it in a small beaker in order to keep it from spilling. He then pipetted 75.0 cm cube of 0.355 mol per dm cube HCl into another test tube. In an attempt to put the second test tube into the second beaker, he accidentally knocks both test tubes together, thereby breaking them and their respective contents mixed up. Deduce whether the resulting solution in the beaker is acidic or basic. One might be wondering, what should I do here? Looking at the question, you need to digest it very well. First of all, you have to write the equation of the reaction. The two reactants are sodium hydroxide and then HCl. So we'll have to write and balance the equation first. We'll give you sodium chloride plus H2O is automatically balanced such that Na is 1, Nb is 1, so the mole ratio of acid to base is 1:1. So we have gotten that fact. We have to you are not going to, there is nothing unknown here. They have given us all the parameters in this formula. CAVA all over CBVB equals NA over NB. What matters here is our ability to interpret what this formula means. To explain this for you further, one should just know that CAVA over here, the implication here is that, you see this CAVA, if you multiply CAVA and divide it by the product of CBVB down here, automatically is supposed to give you the same ratio as dividing the mole of the acid to the mole of the base here. So you see, what this implies is that according to the equation we have here, we have 1:1. That's the mole ratio of the acid to the base. That means that CAVA should be equal to automatically CBVB because 1 is equal to 1. So if we now fix in the values they gave us and discover that denominator is more than numerator or numerator is more than denominator, we will now see which one is in excess. But when they are equal, they are neutral. But from their question, they never mentioned of neutral. They asked whether it's acidic or basic. So we are likely going to see a situation whereby either the CAVA is more than the CBVB, and where CBVB is also more than CAVA. So look at our results. If CBVB is more than CAVA, it means that the solution is basic because this is for base. That's for the sodium hydroxide. But if CaVa, the product of CaVa, is more than the product of CbVb, it automatically shows that the solution is acidic. Reason for this is because it's already established that Na is 1 and Nb is also 1. Let's assume that Na is 1 and Nb is let's assume that Na is 1 and Nb is 2. When we multiply Ca and Va, let's assume we get something like 2. It is also applicable that when we multiply Cb and Vb, we should also get 4, because if you divide 2 over 4, it will still give you this 1 over 2. That's the implication. But in a situation where we have gotten that Na over Nb is 1 over 1, 1 over 1, it means that when CaVa gives us 2, CbVb will also give us 2, so that 2 over 2 is 1. But here, if we multiply CaVa and get something like 3, then CbVb and get something like 2, it means that there is excess acid following this particular reaction. So the mole ratio of the acid to the base is very necessary in answering this question. So let's move ahead and do the solving, because I know the solving is not actually the problem, rather this explanation, so that you can use it to answer similar questions. Remember, you are still on with Her Majesty's World Science channel. So for my explanation, we use the volumetric analysis formula CaVa over CbVb equals Na over Nb. We will now fix the values, which implies that Ca from the question, Ca is for the acid 0.355 times the volume of acid used, 75.0, all over Cb, the volume, the concentration of the base is 0.525 times the volume of the base, which is 25. If this is supposed to give us 1 over 1, from the calculator department, let's check the answer of 0. It's obvious they are not going to be the same, but let's see which one will be topping. 0. What is that? 0.355 times 75. 0.355 times 75 is equal to 26.625. 26.625. If it gives us 26.625 at the denominator and the numerator, it shows none of them is in excess. It means neutrality. But let's check that of 0.525 times 25. 0.525 times 25. This is 13.125. You see, all over 13.125. Automatically, the solution, right, for the examiner, the resulting mixture, I say the solution, the mixture is acidic. Remember, you can, if it is in practical life, you can just use your indicator, but here they are trying to give you values so that you can assess what you are expected to get when you use your indicator from the theoretical calculation. So the solution is acidic. Reason is because 26.625 is automatically more than 13.125, but the mole ratio of the acid to base is 1 over 1. It's supposed to, that it should be that the denominator and the numerator should be exactly the same. So the mixture is acidic, and that's the final answer. So great viewer like you, please, I beg of you, endeavor to subscribe. If you have subscribed, please stay subscribed. Subscribe, and most importantly, share my videos, not only this one. Much love from me to you. I cannot do without you. Best of luck in your exams. Her Majesty's World Science channel is available for you in sciences. Check out the alternative to practical videos in physics and also in biology. Bye for now.
Wait a minute. Have you heard about the Majestic table? It was designed and recommended by Her Majesty himself. Here it is. The amazing thing about the Majestic periodic table is that it provides a clear and colorful classification of elements from P block metals to metalloids to liquid metals. It also shows the boiling and melting points of all the elements. It also has the unique feeling of electrons in the shells of each element.
To enhance the easy learning and teaching of chemistry in schools, in universities, secondary schools, in research institutes. So this Majestic periodic table, demand and special demand, as you can see that space there highlighted, that is where you can include the name of your school, or if you are dedicating it to anybody, you can write there, because you can print it to any size you like. In a majestic size, the resolution will never be affected. So it took me about 3 months to design and provide these informations, but thank God the table is here. What made me to design this is that I discovered that these tables I see in the internet, the one I see in the market, they are not as informative as I want. And then some of them are not updated. Some still retain the fact that there are like, some still see promentum has not been radioactive. Some might see them as artificial element, but it is still is a naturally occurring element, of course. So there are some modifications that this table has been made to include, and that makes it majestic.
This is super majestic.
Much love.